the last week of the course. So I hope that you all enjoyed it. For many of you, many things would have been new, and then must have felt like we have been rushing through things. But then this is kind of an introductory course, which is supposed to have given you a kind of a flavor of the topic. And I hope some of you at least will be able to take it up later and then go deeper into the subjects discussed. So that was the idea here. So today, to start with, before I have received some of your queries, we will address that. And I will also look at the queries that you would put on the this live session chat. But before that, I will give you a kind of brief look at how the particle dynamics affects the cosmic evolution, the cosmology, the universe, and its evolution. Some of you had already asked how this particle dynamics, whatever interactions and then the physics of the particles, elementary particles that we have been discussing would affect the cosmology. So this is what we will kind of very briefly discuss today, and that will also take us to some of the very interesting problems that are not yet solved and which we are all presently trying to find out or address. Okay, so what is universe, and then what are all we doing here? What are the things around us? How these things behave the way they are? How are they originated? All these are questions that we have been asking since the beginning of whatever mankind's history that we know of. The 19th and 20th century, mostly the 20th century, has seen revolutionary developments in this. So presently, all the observational evidence, astronomical, astrophysical, observational evidences point to universe which began at some point and then evolved to the present state. According to the Big Bang cosmology, the universe began as a hot, dense, highly dense, mostly radiation, or just the radiation, to start with only the radiation state, and then all matter in it was created as time evolved, as it evolved. The universe also expanded, and as it expanded, it cooled down. And at some point, as I said, elementary particles were created. The matter was created in the form of elementary particles that we have been discussing. Leptons, muons, which are called electrons, which are basically the light particles, which are called leptons collectively, and quarks. Then, as universe expanded further and then cooled down, These elementary particles could form bound states. The quarks form the hadrons, protons and neutrons and other particles. Other bound states were unstable, as we know. Therefore, finally, when it further cooled down, protons and neutrons could combine to form nucleus, and the nucleus combined further with the electrons to form neutral atoms. And then later on, the different nuclei could combine also. I mean, so the lighter elements could also be formed. When the nuclei were formed, different nuclei of light elements were formed, and then gravity took over, and large-scale structures, gravitational interaction actually brought all these masses in different regions together to form large structures like stars, galaxies, superclusters, etc. So, all the matter that we see around us today, all made of these particles which were created in the beginning of the universe. Nothing other than that could be seen here. So how do we know that all these particles, all this matter that we see around are basically created by these elementary particles, or building blocks are these elementary particles? We had mentioned this in the lectures in different places, but the summary is that we do experiments, and then from the experiments we actually get this information about what are these particles or what are this matter made of. It is similar to the most of this time we can actually think about these experiments as kind of trying to find out things by smashing it. So if you break something, we can see what is there inside. I mean, it's true with a coconut, it's true with your cell phone, it is true with your computer. If you actually break it and then take things apart, then you know what is there inside. Similar thing is done with in Rutherford scattering, for example, where the alpha particles were sent to the gold foil, and it did not smash these things, and then what it gave, it went in near the nucleus, the alpha particles interacted with that and then gave information about it. In the case of proton and the structure of proton, again, electrons, high energy electrons are used, and then it can actually go inside, probe this, and in fact it shatters the proton in the process, like breaking a coconut. So, and we get information about what's there inside, and analyzing this information, these observations, the results of this experiment, we would be able to find out that there are structures, etc. So that's how we find it. So presently we have ample evidence for all this. Whatever the theoretical model that we have been talking about. Okay, we have enough observational evidence to support all these things. So coming back to the particle creation, or the matter creation and the evolution of the universe. So we have presently very good idea about various different stages of the universe, and there are some stages which don't have much of an idea, and some other stages we don't have any idea. For example, how it began, the time d equal to 0, we don't have any idea. We can't talk about that much. In fact, beyond the Planck energy, which is 10 power 19 GeV, we will not be able to really discuss anything much with the present theoretical models, including gravitation or quantum mechanics or quantum field theory, because the quantum gravity need to be addressed there, and then we don't really have a theory for quantum gravity yet. So we don't, in this expansion of the universe or in cosmology, we don't really look at that time t equal to 0. Rather, we will start at some little while later. And that little while is actually not much. It is 10 power minus 44 seconds kind of a thing. Okay. So then 43, 44 seconds, that is what the Planck epoch. So then universe was supposed to be very small and highly dense, as I said earlier, and it cooled down, and then all this some other slightly later time, maybe there was some grand unification theory. So I have not talked about the grand unification at all in our discussions. It's like, you know what is the electroweak interaction? Like we have been combining different forces, like magnetic force and electric force combined to think about as a electroweak force. Sorry, electromagnetic force. And then electromagnetic and weak force combined to give you electroweak force, etc. These are at higher energies, they are actually seen as a single entity, and at low energies, they can be distinctly seen. So if you go further in energy, or which means that in the terms of the evolution of the universe at smaller times in the age of the universe, then we can think about unification of all the forces. Okay, so that's maybe apart from gravity. So strong force, electroweak force, all these things are combined together, and then that's called the grand unification. So this is not known completely. We have some models, but none of these models are verified, and there are no compelling observations to actually go for these models also, where although they have their own, theoretically speaking, they have their own attractions. Okay. But what's quite clearly understood is the electroweak era. That's what we have been mostly discussing in the particle physics part of this course that we have been doing. Okay, it's all that is the time scale and the energy that we can presently explore through experiments. So the Large Hadron Collider experiment, for example, explores these energy levels, these energy scales. And that's what we know about. We can actually understand the particle interactions there at that time, and then we know that our model is quite happily satisfied by all the experimental observations there. Then the hot, okay, so as it taking those elementary particle dynamics there, then we can actually think about what would have happened. So in this, maybe around Planck, after the Planck epoch or within the grand unification period or somewhere, particles were created. So that is how it goes. So all these elementary particles would have been created at that time. And then electroweak epoch says that all these particles should be in the form of elementary particles like electrons, quarks, and photons, of course, radiation, and the W boson and all those things, all the force carriers. Okay, so that stage we have all these elementary particles already there, and then as we go on, the universe expands, and then hadrons are formed around 1 second. Okay. So then between these 10 seconds and then 100 or 100 seconds, nuclei were formed. Nuclei were formed by fusing protons and neutrons, etc. So all light elements were formed at that time. Then there was a long gap. after this thing. Only light elements could be formed because there was a, okay, I don't want to go into that, but there was a hurdle at forming higher elements. It could not be formed because some elements in between, later after lithium, was actually not stable. I mean, it could not be formed in that same way. Therefore, further elements, further nuclei could not be formed. Okay, and we had to actually wait for stellar nucleosynthesis to get the higher elements. Okay, all the higher elements, like all the elements like carbon and iron and all these elements were that we see around are formed in the inside the stars in the stellar nucleosynthesis. Okay, so that we don't want to discuss today. Neither we want to discuss the nucleosynthesis, but there are some other interesting things that we will very briefly discuss. Okay, so at the time of this nucleosynthesis, it's the nucleus that is formed, nucleus of the elements that is formed. It's not yet the atom. So electrons were not really part of this nucleus and then not really bound to this nuclei. This had to wait for a long time, and around 400,000 years, 380,000 is the number that is given, and there was this formation of the atom. So, okay, so this period is called the recombination for some reason. So basically it is the electron which combines, it is the time when the electrons combine with the nuclei to form atoms, mostly hydrogen atom. There were a lot of protons. The electrons combined with the protons and to form hydrogen atom. And then there were also helium nuclei. So then electrons combine to helium nuclei to form helium atoms, etc. And then some little bit of lithium, etc. But what happened is a kind of a dramatic thing there at that time, in that period. You think about the stage where all the nuclei were, nuclei and the electrons were in a kind of a soup, or what we called ions and plasma. Okay, ions and electrons, the electromagnetic plasma, and radiation which existed at that time, the photons which were there at that time, would interact very strongly with this plasma because the plasma is charged and it will interact with the electrons and ions in that. The electrons very strongly interact with these things, and then the mean free path of the photons, if you consider in this kind of a plasma, is very short, very small. So protons cannot really come out of this thing in a way. It cannot freely propagate. Whereas after the atomic formation of the atoms, it is a neutral state, and the universe had now the elements, light elements, which are actually neutral atoms, and the neutral atoms don't interact with photons so strongly. I mean, you will have these absorption lines where you can actually take a particular these things, and that itself has a low cross section. So all the photons are now free to propagate in that. These photons from then on, that is from about 400,000 years in the evolution of the universe, then onwards, it was freely propagating. Okay, it was just moving freely. So these photons should be there. This is one single prediction that was actually later discovered as the cosmic microwave background radiation in the 1990s, and later on confirmed as kind of a black body radiation. I mean, it has a particular wavelength corresponding to a temperature 2.78 at that time. Now it has changed a little bit to more precise value there. And now this is the kind of radiation that we can see now, okay, sitting here, which is coming basically from the primordial radiation or the initial radiation of the universe. Okay, so this is something which actually is fantastic. It is one very strong evidence in favor of the Big Bang cosmology. Okay, it's a kind of a prediction of the Big Bang cosmology, and it has been seen. By the way, this was accidentally discovered. Many of you must have heard about the story, heard this, and later on confirmed. And then now we have really very good picture of this cosmic microwave background. So one of the things that is expected from this, expected of this cosmic microwave background, is that it should be, there should not be any particular direction in which it is coming from. If it is coming from a galaxy or a star or some supernova explosion or something like that, it will be coming in that direction. From that, there is a source, there is a particular direction from which it is coming towards us. And if you look in a different direction, we won't see that thing. Whereas cosmic microwave background radiation is not like that. In whichever direction we look at, it should be there. So that is how we actually have it from the early universe, that we are not any special point. Everywhere else is the same as us. So this is what is called the two principles based on which the cosmology is based, apart from the general theory of relativity, which is called the isotropy and homogeneity. So it is isotropic. It doesn't matter which direction you are looking at, and then it is homogeneous. Doesn't matter where you are looking at it from. Okay, it is the same. And this was indeed so. So all these years, we have been actually improving our observation on cosmic microwave background, and presently we have very good highly precise information about the cosmic microwave background radiation. I don't want to go into the details of this thing, but it is basically the whole sky scanned by the Planck space probe. And there had been earlier the COBE and WMAP, but then the latest one is from Planck mission. And the Planck space probe has actually photographed the entire sky to look, to see this cosmic microwave background. It has taken the picture of the cosmic microwave background radiation coming from this thing, and this is the information that we have. So this granularity, so it's by and large it is isotropic. There is no really special point that you can see anywhere, but at the same time, presently we have a granularity there, which means that there is a small fluctuation of this thing. Okay. These fluctuations can be seen in different ways. It could be density, in terms of density, or in terms of the temperature, etc. So looking at, mostly it is talked about in terms of the temperature fluctuation. And so these different colors actually represents slight variation in the temperature. Okay, it's highly exaggerated in the sense that the temperature fluctuation is very, very small. So 2.73 Kelvin is the temperature overall, and there is a small difference from that when you look at some neighboring points, and that is what is being plotted. The difference is at the order of 10 to the minus 5. Okay, so it's very, very small. So this picture gives that temperature fluctuation. Okay, now what does that tell about anything about the universe? You remember what will happen. Let me go back to that slide. So here, these photons, CMP, cosmic microwave background radiation, is basically the photons which were there earlier prior to this the free propagation. It was there in the plasma of electrons and the ions, right? So whatever dynamics or whatever was happening at that perhaps would affect the spectrum that is propagating, right? So imprint of whatever happened at that time, the physics or the fluctuations or the things that whatever happened in that plasma state or before that would be there in this cosmic microwave background radiation that we see today. So the fluctuations can be seen in a way as the kind of fluctuations or the perturbations that has happened or that is there, that was there in the plasma before that. Okay, and what could that tell us? What are the things that would affect that? So certainly, what are all the matter that is there in that? What is the energy, total energy of that? What are the other, ions, how much of ions were there, electrons were there, and if anything else was there, then all those things would affect this fluctuation or this cosmic microwave background. That's the basic idea. Now, going from that, one can actually analyze this powers, this in terms of this fluctuations, in terms of expanding that in terms of this spherical harmonics. What do I mean by that? If I hope many of you, at least whoever have taken up the quantum mechanics, are familiar with the what's called the spherical harmonics. It's a function usually of the two angles, theta and phi, the two polar, or the polar angle and the azimuthal angle, and similar to the trigonometric function, sine theta, cos theta, etc. These are also what are called the orthogonal functions. Okay, if you don't know about orthogonal functions, it's okay. I can very briefly tell you what is the meaning of that. You see, think about the usual vector, momentum, spatial coordinate, or the vector, 3 vector. Okay, and A, the magnetic moment, potential A, or magnetic field, electric field, etc. All these we can express in terms of some basis vectors. Usually that is what we do. We go to either Cartesian vector space and express E, electric field E, as Ex x cap plus Ey y cap plus Ez z cap, etc. So these x cap, y cap, z cap are the basis vectors. So any arbitrary vector we can represent in terms of these basis vectors. In a little similar way, we can actually think about these kind of things in the functions also. So some kind of a function space rather than the vector space. Okay, so where again any arbitrary function can be represented in terms of these basis functions, and these basis functions are called the orthogonal functions. Okay, same way as x cap and y cap are orthogonal vectors. Okay, so here also we can represent these any arbitrary function in terms of orthogonal functions. This is what is done in Fourier transform. So the Fourier transform expands any function in terms of the sines and cosines, sine function and cosine function, and it's not the sine and cosine are not the only orthogonal functions. Spherical harmonics are other set of this one. There are other orthogonal functions as well. So functions can be expanded in terms of other orthogonal functions also. Similar to saying that x cap, y cap, z cap are one set of orthogonal functions. R cap, theta cap, and phi cap are another set of orthogonal basis vectors that we can choose. So similarly here we have the spherical harmonics as the basis. So This fluctuation in thermal fluctuation, let's take delta T, can be expanded in terms of the spherical harmonics. Once we do that, we get a lot of information and we plot this, and in terms of this L, again, let me don't go into the details. You can learn that and then understand it later. So basically, I will tell you what are the information that we actually get from these things. So we can look at this, what's called the power spectrum of the cosmic microwave background, and then get information about what is the total energy content of the universe and how much of baryons. See, most of the matter, when we talk about the matter in the universe, we can kind of neglect the electrons because the mass of the electron is very small. So it's basically called the baryon content. The proton is 2000 times heavier than an electron, so we can neglect the electrons in that way. So that's why it's called the baryon content. Okay, so the all matter which we are familiar with, all matter that we are familiar with, as we said in the beginning of today's discussion, that all are made of these protons and neutrons, etc. So these are the baryons, and this baryon content is only 5% from the power spectrum analysis of the CMB. But the total matter apparently should be 32%. So which means something like 27% is unknown to us. And this unknown matter is what we call dark matter. So we have 27% of dark matter, which we don't know anything about, and 5% is the baryonic matter. And rest of the 68% about is basically the dark energy. Okay, so the dark energy of the universe is quite a lot, and then these things are like and the dark matter itself is 27%, which is dominating compared to the non-matter content of the universe. Okay, some numbers. I will leave this. I will not go into through this slide in detail, but but I'm going to share this some to you later. So basically, I just want you to see what's there in this red rectangle. So this says that the baryon to photon ratio is something like 1 in a billion. Okay, so that is the number that we get from the cosmic microwave background in that. Okay. So now I will come to this a little bit more about it a little bit later. But before that, let us see. Let me tell about how the particles are created, and then there is a reason for this thing. Okay. So, what is our understanding of how the particles are created? How can that be possible? Quantum mechanics talks about small particles, atoms, electrons moving around nucleus, etc., or even subnuclear particles. And it can very efficiently describe the atomic scale phenomena, okay, dynamics at that stage. But it can't deal with creation of particles. It doesn't really talk about electron being created. It can only talk about electrons which are existing in the atoms and the protons or nucleus which is existing there. It doesn't talk about the creation of a particle or annihilation of a particle. This had to actually wait for the, or it was already there, but wait for combining the idea of special theory of relativity with quantum mechanics. So special theory of relativity said that the energies and matter, mass, are related to each other. So this is one of the things that one of the most famous equations, E is equal to mc square from Einstein. And that's the kind of thing that we have seen in atomic energy creation and various, or in the, when we discuss, for example, the binding energy of the nucleus, etc., we already saw all these things. That energy can be formed into matter, matter can be formed into energy. But it can also create new particles. So that is where the quantum mechanics combined with the special theory of relativity in the form of what's called the quantum field theory allows us to do. So where there was no electron prior to it, we could create electrons. We could have electrons. This is what, for example, happens in beta decay. So beta decay cannot be explained by pure quantum mechanics alone, the usual quantum mechanics. We need quantum field theory for that. So there, electrons and antineutrinos are created. So we will see in this kind of picture, as per the quantum field theory, that various things can actually happen. It can actually annihilate electron and positron and create entirely new, entirely different particles, muons and anti-muons. And as I said, in weak interaction, it can actually create electrons and neutrinos, etc. So quantum field theory allows existing particles to be destroyed, creating new particles. That is how we understand the particle physics. Okay. And within the quantum field theory, it is necessary to introduce what are called the antiparticles. Okay, antiparticles are they have similar properties compared to the particle itself. So, for example, electron, if you take the mass of the particle electron and its antiparticle positron are the same, but the charge, electric charge, is opposite. There are various other different quantum numbers which can be opposite. The lepton number is opposite, etc. Similarly, for quarks, every quark there is an antiquark that we can think about. So for every particle, there is a mirror or an antiparticle that the quantum field theory demands, in fact. Okay. So this is one thing. And when particles are created, when we talk about creation of particles or matter, it's always in pairs of particles and antiparticles. So electron and positron, U quark and anti-U quark, okay, D quark and anti-quark, D anti-quark, etc. One of the reasons is the charge conservation here. You cannot have suddenly charge popping, electric charge popping up. That's one of the things. So similarly, lepton number and all other quantum numbers which are conserved are to be conserved. Okay, baryon number conservation, etc. This is true with when particle matter is actually annihilated also. Particle and antiparticle are annihilated to each other. So now if particle and antiparticle can be annihilated, if they are created in pairs and annihilated in pairs, then we don't really would be seeing these particles, because if there were particles created and they could also annihilate, finally we will only see some radiation. So it will all annihilate in that way. But we already saw that, we all exist, various different structures in the universe exist. So particles, and we are all made of particles, not antiparticles. So there are some point particles somehow survived and antiparticles did not. Okay, and we know our Big Bang nucleosynthesis, the combination of these protons and neutrons, etc., to form the nuclei, light nuclei. And for this to happen, we need a specific number of this baryons, the particles, not the antiparticles, or particles over the antiparticles, okay, compared to the number of what we said, something like a billion, 1 in a billion. So for every 1 billion photon, there should be one baryon, okay, not antibaryon. a particle, not an antiparticle. This is what we need to have the Big Bang nucleosynthesis, and that's what we need further on for all the structures in the universe. And this number, by the way, what is required for the Big Bang nucleosynthesis is the same as that we see from the power spectrum analysis of the cosmic microwave background. And that's again another great success of this Big Bang cosmology. These are two different independent ways of looking at it, and then the numbers agree. So, as I said, there is a little bit of an asymmetry in this dynamic somewhere, which allows a small fraction, small in the sense that it is 1 in a billion, of the baryons or the particles to be left out in the universe after combining with or the interactions with the antiparticles. Okay, and how does this happen is something which we still don't know, and this is one of the mysteries which are to be solved. Particle physics, present understanding of the particle dynamics, the standard model of particle physics, does not have an answer to this thing. It cannot accommodate this. Okay, sorry, in this slide it is not 0 power 9, it is 10 power 9 photons. Somehow that one is missing. Okay, so this is one of the things that the baryon asymmetry of the universe is something which has to be understood. Okay, let me quickly go through. I think I have to speed up a little bit. So the other thing that we have here is this unknown matter that I talked about earlier. The baryon content is only 5%, but the total matter content is 32%. So 27% is not known to us. And what is that candidate? So this is also something which we don't know. Apart from the CMB power spectrum analysis and the evidence, the numbers that we know from that, there are other evidences of dark matter from entirely different places, like from the galaxy, rotation curve of the galaxy. So we have what is expected if all the matter in the universe is in that galaxy is seen from the observed luminous stars. Okay, so the galaxy is made of stars, and then of course there could be planets, but they constitute very little mass. So mostly it is star mass. So you count the number of stars and then typical mass of stars and then multiply it by that. That will give you the mass of the galaxy. And then it's seen that it is basically expected that as you go away from the center of the galaxy, the mass actually goes down and then you don't have mass at the periphery. If you take that picture, then you will get, because of, I mean, if the stars at the periphery will be rotating. It's like the planets rotating the sun, rotating around the sun. Similar to that, the stars around the galaxy is rotating. The velocity, the speed that is required for this thing to balance the gravitational pull is basically what we will look at as the rotation speed of the stars. And at the periphery, if you look at that, what is expected is kind of a 1 over r behavior, that as you go away from this thing, then it will come down. But what is seen is not so. So this is indicating that there is other matter in the non-luminous matter there. So this is again called the dark matter. It must be the same. And there are also other lensing effect and things like that that we have seen. Okay, let me not spend time explaining this. I will leave it to the curious minds to actually look up or send me a mail. And particle physics candidates are being explored, but we don't have any kind of clear idea, but we have many different proposals. There are various different experiments, including direct detection experiments dedicated to find the dark matter candidates. Basically heavy nucleus, when the dark matter, if we are all passing through dark matter, they will hit the heavy nuclei, and then the recoil of that in a controlled way can be analyzed, and then if that is there, then we will see it, but we have not seen it yet. Then LSC is looking for production of the dark matter. Dark matter is invisible, we don't see it, but associated to the dark matter production, there may be some photons which are emitted. When looking at these photons, then we would be able to see this thing, and there are other ways of looking at this at the Large Hadron Collider also. Okay, so Large Hadron Collider itself, I have some slides. Again, I don't really want to go in, some information I wanted to give to you. So these are all given here, and you can go through it. It has some very state-of-the-art magnets, dipole magnets to bend the protons around the tunnel, and then the detector itself is something which we had already discussed in the course, the Atlas detector, which is huge and complex and with all kinds of things in it. So there are some other information here as well. I thought I will put this so that anybody who is interested in can just go through it and then see. If you have questions, you can ask me. I don't want to discuss it today. Okay, I will. So basically, we talk about how things are. When we say we have discovered a Higgs boson of 125 GeV mass, what do we mean by that? How do we know that it is 125 and not 200? Things like that are kind of indicated and then expressed in this thing. And okay, so let me end this and then look at your chats a little bit. So what we have presently is a good amount of understanding of elementary particle dynamics. So we know quite a lot about how they interact and then what happens to these particles when they talk to each other. But there are still some missing links, crucial missing links that has to be found out. So this, for example, the dark matter, the baryon asymmetry, there are also many other small these things. So the mass of the neutrino and the Higgs mass is known now, but the stability of that against the quantum corrections, forget about it if you don't know what it is. But for those who are somewhat familiar with it, and the stability of the vacuum and things like that are kind of not technical difficulties again. So these are all being explored at the moment. So that's where we stand. We have a kind of picture of the universe built from our understanding of particle dynamics, along with the gravitational understanding of the gravitational interactions and the cosmological principles, etc. But there are these missing links which has to be fixed. And quantum gravity is one another thing which is still in the very, very early stages of our understanding of the. There are different proposals, but we still don't know. String theory, for example, you must have heard about, is one of such one way to look at things beyond the particle dynamics. So, but there are, it may be, and it can also address quantum gravity to a good extent, but there is still, it's not yet in a form where we can actually make any kind of connection with the experiments or observations and then prove or disprove any of those predictions, etc. Okay, so that's where we are, and then let me now look at, so let me leave the earlier slide there, and maybe this and this, and then look at your charts. questions. Okay. So the questions that some of the before we go into again specific physics questions, general information, because many of you have been asking about the exam. We will put up announcement very clearly in the coming days, but basically the exam is going to be, the questions in the exam are going to be very similar to the assignments in the exactly similar fashion. In fact, there will be some of the questions from the assignments itself. Okay, all those 12 assignments we have had, some of those questions will be repeated in the exams as well, and there will be similar questions, many other similar questions in that. So that's about the exam. And some assignments wherever we had to reevaluate, we have already done it. Sometimes it takes a few days to actually, because the technical team handling this is handling many different courses, so they they will take their time. We will have to actually find out and convey to them, and they take their, I mean, all this process sometimes get a little bit delayed. So don't worry about this thing. Whatever we have said that we would be reevaluating would be reevaluated and then put up there. Even in the exam, I think at some point you will have you can actually send your comments about the questions, okay, immediately after the exam, and we will be looking at that as well. Okay, so let me quickly look at the questions. Specific questions, like, okay, there are some questions on dark matter, etc., which I think you send me a mail or put it in our forum discussion, and we will discuss that, because time is short now. I will not be able to go into the details, but I'll be very happy to actually discuss this over email or over the forum. Okay, both our team will be able to happily discuss that. Why are the 3 generations of cars? And yeah, so there are some of these questions are, why 3 generation is still a mystery, we don't know. That's kind of an observational fact presently. Okay, why can't we have more particles? Well, we can still have, and there are ways people have actually accommodated or thought that some of the problems can be addressed by adding more quarks and more leptons. So that is what is being done, but we don't have any evidence of new particles, etc. Neutrinos formed even before the atoms after the Big Bang. Yes, neutrinos are formed along with the elementary particles. It is one of the elementary particles. They are there. They were there in the electroweak era. So if you look at that chart, that slide, which I will share with you, it is much earlier than the atoms. Okay, it's not that the beta decay atoms, neutrinos were created in the beta decay. These neutrinos which are created in the beta decay, etc., are very small fraction of the neutrinos that we have in the cosmos otherwise. Okay, but basically most of the interstellar most of the stellar processes, okay, generate these neutrinos. For example, the solar processes, okay, solar nucleosynthesis creates the pp chain, etc., creates a lot of neutrinos. So you have a lot of neutrinos coming from the interior of the, or from the nucleosynthesis that is happening inside the stars, including the sun. Okay, those are the sources of these things, not really the beta decay, although beta decay also gives some. Okay, then CMB comes from Big Bang, but it should be a long gone as it was a long period of this thing, and then why it's, yeah, that is the beauty of the whole thing, right? We are all made of all those particles which were created billions of years ago. Okay, billions of years ago. The protons that exist in our body are from billions of years ago, created in the early universe. Similarly, the photons that we see in the cosmic microwave background are from those era, that era where it was created, something like when the universe was much younger, some 400,000 years compared to 13 billion years or 14 billion years. Okay. But the only thing that has happened is, since universe was expanding, it stretched, which means that its wavelength increased, or the frequency decreased, or the energy of the photon is decreased. So that's why we see the energy at the moment as corresponding to 2.7 Kelvin. Okay. Can W bosons take part in electromagnetic interactions? Yes, they can. W bosons are weak particles, but they have charge, electric charge also. Whereas Z bosons do not have electric charge. They cannot take part in electromagnetic interaction. Any particle which has electric charge will take part in electromagnetic interaction. So W bosons, although are weak gauge bosons, they do interact electromagnetically. What is the exact size of an electron and quark? Well, we don't know. I mean, for all practical purposes, they are point particles. They don't have any size. But of course, in quantum mechanics, we can't talk about zero size or a precise size. Okay, so we can only talk about a kind of uncertainty, a range of this size. Okay, so whether electron is a point particle or it has a structure, what is the size of electron, what is the size of proton, etc., are still being probed. So as of now, the size of the electron is less than 10 power minus 18 meters. Okay, and quarks also are supposed to be the same. Quarks are even more difficult because we don't see them in free state. So it's all kind of, it's as good as saying that their size does not really come into any of this dynamics. So we can consider them as point particles for all practical purposes. Okay, I think we will kind of stop our discussion here, and the other queries I will try to send you the some kind of a reply, and if you don't get any replies, then you can also send me an email to remind me so that I can send you the answers or whatever thoughts that I have on the query. Okay, so thank you all very much once again for joining the course and to be there today in today's discussion as well. And I hope you have got some kind of flavor of what's particle dynamics, and then what kind of a thing is happening in the, what kind of a model that we have for the nucleus, and what's our present understanding of elementary particles, etc. And I hope all of you will go further, deeper into this, and then learn more. And then some of you, I wish also success in becoming an active researcher in taking up some of these problems that we still are puzzled with. Okay, thank you.